Now we already know what's a functional, we already know what's a functional derivative and how we can calculate them. But we are going to derive here a very useful formula to calculate the first order functional derivative for one particular case. It's a particular case, but it's a kind of quite common in physics. That's why it's going to be useful. We're going to consider that in this case we'll call rho, it will be the function where this function will depend on, and the functional, which will depend on rho, we'll find in this way. We have the integral over the whole volume of some function that depends on the spatial coordinates, depends on rho, and we'll also consider that it will depend on the gradient of rho. So in order to extract a general expression for the first order functional derivative with respect to rho here, we'll follow the definition. And the definition of the first order functional derivative is actually it's actually going to be related with the first order in the Taylor expansion when you change rho with rho plus epsilon times eta. With epsilon, it will be an arbitrary, it's an infinitesimal, and eta is an arbitrary function. But here, the function just not depends on rho, but also depends on the gradient of rho. So therefore, we also have to change not only rho, but also we have to change the gradient of rho with that one, the gradient of rho plus epsilon times the gradient of eta. And now we have this function here. We'll have to make, in order to make the Taylor expansion, the first order derivative with respect to epsilon. So we have to make the first order derivative with respect to epsilon here and consider the term where epsilon is equal to 0. So there are two different sources in order to calculate the first order derivative with respect to epsilon. The first one is coming from here and the second one coming from here. We'll apply here the chain rule in order to calculate the first order derivative with respect to epsilon. So therefore, the derivative, the contribution to the derivative coming from this term will be the partial derivative of f with respect to rho times the derivative of that with respect to epsilon, which is eta. Then we have, similarly, we can, the next term here will be the derivative of this with respect to epsilon coming from this second term here. So we have to make, therefore, the functional derivative of f with respect to the gradient of rho times, which is the scalar product, the gradient of eta. So here we're again applying the chain rule. So now we have made the derivative with respect to epsilon, and we can compare this term here with this term, so that in order to extract from here the expression for the first order derivative with respect to rho. So in order to do that, it's important to have eta to be isolated, as it appears here. So here we have like two different contributions. In the first one, yes, the eta is isolated, so it's clear that one contribution to the first order derivative of f with respect to rho will be that one. However, in the second term here, there is no eta, it's not isolated. What we have is that instead of eta, we have the gradient of eta. So we have to manipulate this term here in order to have eta isolated. And that's what we are going to do next. We are going to manipulate this term in order to isolate eta here from here. So that was the term that we had, the expression that we had before. And now we are going to two different steps in order to isolate eta from here. So from here to here, in the first step, we are going to apply the product rule for divergence, which basically says that the divergence of a vector times a function is defined in this way. Okay, so as you can see here, this term here is actually this one, so we're going to substitute this one with these two terms. So this one will be substituted with these two terms. So the advantage of doing that is, as you can see here, we have in one of the terms, in this one, you have the eta is already isolated. This is good in order to compare with the first of the functional derivative definition, because therefore from here we can also deduce that we'll have another contribution to the first order functional derivative will be this one here. But we have an extra term here where eta is not isolated because it's inside this divergence term. So in order to analyze this contribution to the integral here, we'll apply the divergence theorem or the Gauss theorem, which basically says that we can substitute the integral over the whole volume of a divergence with the flux over the boundaries of this vector. So we have the flux over the boundaries of this vector here. This vector is this one times eta. And we consider a condition that eta has to satisfy. So eta in the boundaries, so we consider very huge boundaries because the volume we consider to make the integral will be infinite. So the boundaries we consider is will be in the infinite. So we'll consider that eta in the infinite will vanish. This is reasonable to do for the physical functionals that we'll be using, in the sense that this rho here could be the charge density, for example, and the charge density has to satisfy some kind of constraint. For example, the integral over the whole volume should be the total density is a fixed number. And when you change and you modify this function in order to calculate the functional derivative with this term, this modification on the function on the density has to fulfill also this condition. So therefore, in order to fulfill this condition, this whole integral, in order to the whole integral to be, or the whole volume to be a fixed number, these constants should be vanished for when in the infinite. So when the volume is getting larger and larger. So that's why you need that this eta should vanish at the boundaries, because otherwise it will not satisfy the constraint that usually this kind of rho for the physical situations has to satisfy. Therefore, considering that rho vanishes at the boundaries, this term here has no contribution in this integral. So we just have these two terms. So, and as you can see in both terms, this eta is separated, and from here you can easily deduce which is the expression that we have for the first order functional derivative, which is this one, which is the expression we have here in the square. So now we have derived a quite useful formula that whenever you have a functional that depends either on rho, on some functional, or on in its gradient in this way, you can apply in order to calculate the first of the functional derivative with respect to the function to rho in this case, which is quite useful actually. Actually, you can follow some similar procedure in order to have expressions for the higher order derivatives as well.